Hello friends, welcome back to the S&W audio channel. In the previous video, we discussed the basics of how to measure distortion in LTSpice. In this video, we will do a demonstration. In the last video, we came up with 6 practical recommendations for doing a harmonic distortion measurement in LTSpice. These recommendations included turning off compression and storing data in double precision, simulating an adequate number of whole cycles, choosing an appropriate number of FFT sampling points, matching the input waveform time step with the FFT sampling interval, ignoring an adequate number of output cycles, and being careful with long time constants in the circuit. These 6 recommendations led to the following setup, which we will put to the test in our LTSpice demonstration. Let's now turn to LTSpice to see our setup in action. So I've gone ahead and loaded the distortion setup here in LTSpice. As you can see, we've got the circuit up here, we've got the input reference sine wave, we've got the Honey Badger, which is our device under test, and we've got here some of the extra circuitry for the Honey Badger, including the load, the supplies, and my measurement gizmo, which I don't think we'll be using in this demo. In the slide, actually, I did not include this stuff just for clarity, because all the important stuff actually is here on the left-hand side. I've also have the parameters that set up the input waveform. These include the frequency and the amplitude. And I have like a very basic transient command here. Everything that you see in blue is commented out and it's not doing anything. So right now, I've got the input frequency for the sine wave set at 1 kilohertz with a 1 volt RMS amplitude. That's why 1.414, which is the square root of 2. And the transient is set up to start sampling the data at time 0 and then capturing 1 millisecond of data, which at 1 kilohertz translates to 1 cycle. So given that we haven't done any of the considerations, we should expect an FFT that is going to look terrible. Also, for this first section of the demo, I'm going to focus just on the input sine wave, and then we'll deal with the amplifier stuff. All right, so let's go ahead and get it running. So I'm just going to go ahead and run. It's pretty fast. And if we look at the reference or the input sine wave, we can see it's 1 cycle as we expected. To see the FFT, what you need to do is you right click and you go to view and look at FFT. And then make sure that you select VREF, which is the output of our input sine wave. And you hit OK. And here it is. And you can see that literally what we got is garbage. If you can make anything out of this, I really commend you, because I really can't. You can see that our noise floor is very high. We get some screwed up images. The frequency bending, or the frequency resolution that you get here, is 1 kilohertz. You can see that the FFT couldn't process anything below, and the points between each process in the FFT, you can see is 1 kilohertz, right? We've got a point here at 1 kilohertz, one at 2 kilohertz, one at 3 kilohertz, and so forth. This is terrible. So you can see that why we need to actually take those considerations that I spelled out earlier quite seriously. The first thing that I'm going to do now to improve things is I'm going to sample 10 cycles. So our sample window was 1 cycle in this first iteration. Let's increase that to 10 cycles. So say OK. And I'm just going to run. OK, so we got 10 cycles now. So things should be a little bit better. At least the frequency resolution should be better. So we should go from 1 kilohertz frequency resolution to 100 hertz, right? 1/10. So BREF. So immediately you can see that things got a lot better than before. Our noise floor is still kind of high, but you can see now that we are at 100 hertz rather than 1 kilohertz where the FFT starts. You can see that the bin now is 100 hertz. So the point that goes immediately after 1 kilohertz is now at 1.1 kilohertz rather than 2 kilohertz. So that's already pretty good. But we still got this like funny stuff, right? Like if this was a pure sine wave, we should only get this spike and nothing else. Like any of this stuff should not be there. So let's keep building on top to see how things get better. So let me just close this. So the next thing I'm going to do is I'm going to turn off compression, and I'm going to tell LTSpice to store data in double precision. You can look up on Wikipedia what double precision is, but in simple terms, it just tells LTSpice to store more decimal places. So I go from comment to spice directive to activate it, and I'm just going to go hit and run it again. So again, we get our 10 cycles. I mean, principle should look the same. So let me just go to view and FFT and that. By turning compression off and by setting the storage data precision to double, we can see actually the noise floor has gone down, but we still have all these images at high frequency. So we still got more work to do. So let me just close this and let's take it to the next level. So now what we need to do is we need to match the time step, which is the time interval between calculated data on the input waveform, and we need to match that to the sampling rate, which is every time the FFT takes a sample of the input waveform. And to do that, what we said we were going to do is we're going to force the time step to be equal to FFT step max. Now that we have added FFT step max to our transient command, we need to tell LTSpice what FFT step max is. To do this, I'm going to uncomment this section. So I just go here, spice directive, okay. And what I'm doing here is I am calculating FFT step max just the way that I described it in the previous video. So if you remember, FFT step max is the number of cycles that we're capturing, FFT cycles, in this case 10, divided by the input frequency, in this case 1 kilohertz, defined up here, divided by the number of points that we're going to be sampling. If you remember, in the previous video, we said that the default value for the number of points is 2 to the 16. I decided to bump it up to 2 to 18 just because my PC seems to be able to handle it, so that's completely fine. Now that we have these parameters defined, let's go ahead and run the simulation. Now that the simulation is running, notice how much slower the simulation is. This is because now we are forcing the simulator to calculate data in increments equal to the sampling interval FFT step max, and this interval is much smaller than the default max step value. Again, we do this to match the simulation calculated data to the sample data. So now that this is done, we can go ahead and view our FFT, and by now it should look very nice. Before we continue and look at the FFT, I want you guys to pay attention to this number here. This is the number of FFT points that LTSpice will use to calculate the FFT. This number needs to match our variable FFT points. In our case, we set the variable to 2 to the 18, which is equal to 262,144 as written in the box, so we're good to go. Having said that, let's continue. And look at that. We only get a single spike at 1 kilohertz. The width of the spike is the 100 hertz. That is the frequency resolution. The noise floor is at minus 320 dB, which is really good. And we got like almost no images at high frequency. So this is a clean FFT for an input sine wave. Now let's turn our attention to the output. If I go ahead and plot it, we can see it right here. And it's a waveform of about plus minus 55 volts or so. So to see the FFT, we just do the same process. So we go view, FFT, and this time it's V out. So hit OK. And we can see that it looks kind of funny, right? I mean, it doesn't have images, but we can see that sloping noise floor. We can see that there's a blip here, which it's already hinting us that there's distortion that is getting masked. And then the noise also in the midband is kind of high. And this is a consequence of two things. This rising noise floor, we know it has something to do with the low frequency time constants of the circuit. And this high noise floor in the midband has to do with not waiting for the transients of the amplifier to settle out. So let me just close this. To enable our waiting time, all we have to do is, in this case, I need to uncomment my more complete transient command that includes the waiting cycles and the capture cycles. So just go hit OK. And then I just need to comment this one, which we don't need anymore. So now that I've done that, I'm going to just go ahead and run. And this is going to take some time. So I'm just going to cut the video. Now the simulation is done And actually what LTSpice has done is has simulated 10 milliseconds. It has then discarded that data and then simulated another 10 milliseconds. So if we look at the output and then we view at the FFT, hit OK, we can see now that that midband noise is gone. And the only thing we get is that sloping noise floor, which we know it has to do with the low frequency time constants. And again, it's still masking the distortion of the amplifier, so we need to get rid of it. So let me just close this again. And to get rid of the low frequency time constants, we need to go into the Honey Badger amplifier itself, and we need to short out those low frequency capacitors. So the first one we need to take care of is the input coupling cap. And the second one we need to take care of is the capacitor in the feedback network, which it is, where are you? It's right here. So I'm just gonna go short it like that. Okay, so now that we've done that, we can go back to our setup and I'm just going to rerun it. Now that the simulation is done, let's look at the results one last time. So again, view, FFT, okay. And now that is the true distortion of the amplifier. We get our spike at 1 kilohertz, the second harmonic at -90, the third harmonic at -95 or so, and then the high frequency harmonics. So by following the guidelines, we've actually been able to get a very clean FFT of the amplifier. Now that we have a clean FFT, what we also need to do is compute the THD of the amplifier. To do this, we're going to use the .4 command. .4 actually stands for Fourier transform, and what this command will do is take those harmonics and compute THD for you. The command takes 4 parameters. It takes the fundamental frequency, FREQ. It takes the number of harmonics that it's going to use to compute the THD. 9 is actually a good recommended number. It takes the number of cycles of data that were captured in the output waveform, and it also takes in the signal that it's going to be evaluating. To look at it in action, let me just uncomment it and rerun the simulation. Now that the simulation is done, to view the results of the .4 command, we need to look at the error log of the simulation. So if we scroll down, we're going to see this result right here. And what the .4 command is doing, it is calculating result information for each harmonic. So if you look at it here, you'll see the number of the harmonic, its frequency, what its Fourier component is, which is essentially the amplitude, the normalized component, the phase, and the normalized phase. But probably the most important part is that it calculates the THD, or total harmonic distortion, which for the Honey Badger at 1 kilohertz full power translates to 0.000108%. Now let's say that you wanted to compute the distortion at more than one frequency in order to be able to plot the distortion over a continuum of frequencies. To do this, you can actually use the step parameter as I showed down here. So let me just go ahead and uncomment it. And what this parameter is doing is going to tell LTSpice to repeat the distortion simulation over this list of frequencies, which include 1, 2, 5, 10, and 20 kilohertz. So this is going to be a long simulation, so let me just go ahead and run it, and we'll be back when it's done. Now that the simulation is done, we can again see the results in the error log of the simulation, and we can see that the simulation has run 5 times. Here's the first one for 1 kilohertz, the second one for 2 kilohertz, the third one for 5, the fourth for 10, and the fifth for 20 kilohertz. And for each one, the .4 command has given us the distortion. If you want to go ahead and plot this, what I've done is I've created a Excel spreadsheet that combines all these results. So let me just show you how it works. Switching to Excel, you can see here's the spreadsheet that I use. And what it is just a simple spreadsheet where you can take all the .4 results and copy them into this space here. Everything that is in blue is where you would stick raw data. And then it takes all these results to compute these tables shown here, which then are grabbed by the charts in the following tab to plot our results as shown here. So let's go ahead and copy the results from our simulations into the raw data so you see where you need to paste everything in order to see what the distortion looks like for the honey badger. So if we go back here, which is the error log, I'm just going to go ahead and start copying the results one at a time. So just go like that, Control C, and paste it for 1 kilohertz. Then go to the next one, go here, Control C, and copy it for 2 kilohertz. And go back here and take the one for 5 kilohertz and copy it here. Keep scrolling down. Then go for the one for 10 kilohertz and copy it here. And then finally the one for 20 kilohertz and we copy it right here. Okay, so now all these new results get crunched here into something that you can plot, and that's plotted here. Now you can see that the plots don't look too nice, so we need to readjust the scales. So let me just go ahead and do that. Now I've gone ahead and adjusted the axes, so now you can see how the distortion of the honey badger looks over frequency. I know that the data in between the dots is interpolated, but at least it gives you a feel on how the distortion looks like. And in this case, we can see that the total harmonic distortion up to 10 kilohertz is mostly following the second harmonic, and then after that it follows the third harmonic because this one becomes larger than the second. With this we conclude the demo section of this video, and as always I'll be sharing the materials that I have shown. In the next video we go back to a bit of theory and cover distortion in resistors. Additionally, we will finish the part selection of the input network components. If you have any questions regarding the content of this video, feel free to write questions and comments in the comment section below. If you like the content of this video and want to get notified when the next video is available, please show your support to this channel by subscribing and hitting the thumbs up button. Thanks for watching. Until next time, goodbye.